Can you hear me all right?
Yeah, absolutely.
I'd like to thank Chris Budd for inviting me to give this talk on graph theory. It's mainly historical and is designed to be elementary, but hopefully some of it may be new to you. Next slide, please. Next slide. In this subject, most of the ideas arose not from applied mathematics as such, but either from humbler origins, such as from recreational puzzles, or from the sciences and social sciences. And after showing how the study of graphs and trees arose, I'll move on to interval graphs before concluding with some well-known problems from operations research and a brief mention of computational complexity, where graphs have played a significant role. Next slide, please. As a starter, you'll all be familiar with the Königsberg Bridges problem, where the 4 regions of the city were linked with 7 bridges, and the citizens wished to take a walk crossing each bridge exactly once before returning to the start. The impossibility of doing so, as you all know, was demonstrated by Euler, whose diagram on the right showed that the problem was a topological one, where only the connections between the regions mattered. And by counting the bridges around each region, and noting that whenever we enter a region, we must be able to leave it again, he reasoned that all these numbers must be even. But for Königsberg, the numbers are 3 and 5, and so no such walk exists. What Euler did not do was to draw this 4-vertex graph and show that it cannot be drawn in one continuous pen stroke without repetition. His argument was purely on counting bridges, and this picture, or graph, did not appear for a further 150 years. And even the organizers of the International Congress of Mathematicians in Korea in 2014 got it wrong when they featured this graph and headed it Leonhard Euler. But even so, this problem is now considered to be the earliest in graph theory because it eventually gave rise to the concept of a graph consisting of points or vertices joined by lines or edges. Next slide, please. And we're now used to representing geographical features topologically, such as in the familiar London Tube map, this one dating from 1933. And again, the distances and the straightness of the rails don't matter, only the connections between the various stations. Next slide, please. Following on from the Königsberg problem, which gave rise to the mathematical study of Eulerian graphs, where every vertex degree is even, is this problem named for the Chinese mathematician Meigu Guan, who solved it in 1962. Here we want to deliver letters in a network of streets, repeating them where necessary, but covering the least possible total distance. And in this particular example, with just 2 vertices, B and E of odd degree, we can minimize the total distance by finding the shortest path between them and doubling the edges along this path. This then gives us an Eulerian graph with all of its vertices even, which we can then trace as before. But when the number of odd vertices is much larger, the problem becomes much harder, but it has been solved and efficient algorithms are known. Next slide, please. Our last recreational origin is on the ancient topic of maze tracing. Given the maze, such as the Hampton Court maze here, we can draw a graph showing the possible choices at each stage. It's in the middle. And from this, we can easily spot the various escape routes. But of course, this doesn't help you if you're stuck in the middle without access to the whole map. But in 1895, the Frenchman Gaston Tarry gave a rule for escaping from a maze and presented an algorithm for doing so. And this was one of the earliest algorithms for solving a graph theory problem. You'll see others later. Next slide, please. We now turn our attention to trees, and these lead to many interesting problems in pure mathematics, especially where enumeration is involved. Here, a tree is a graph containing no cycles, and they come in various forms. Above are the 6 unlabeled trees with 6 vertices, but how many unlabeled trees are there with 100 vertices? And how many are there if the vertices are labeled, as shown below on the left? or if we consider rooted or branching trees as shown on the right. For some reason, graph theorists often put the roots of their trees at the top. Next slide, please. Such a question even appeared in the film Good Will Hunting, where the challenge, described in the film bizarrely as a difficult problem in functional analysis. The challenge that was solved by the janitor, Will, was a simple one of counting homeomorphically irreducible trees, that is, those trees with no vertices of degree 2. Next slide, please. Here are some examples. Among branching trees are family trees, and below is an administrative hierarchy. On the right are the 3 chemical alkanes, C5H12, with 3 carbon atoms. But how many alkanes have 50 or 100 carbon atoms? And below is a practical problem of designing a gas pipeline network in the Gulf of Mexico. Construction costs, it had to be a tree, but which of the many possible tree networks is the cheapest? Next slide, please. One of the earliest origins of mathematical trees arose from Kirchhoff's writings on electrical networks. In 1845, he introduced his fundamental current and voltage laws for a network, with the flow into each terminal equaling the flow out of it, and the voltage difference around each cycle being 0. But for the second of these laws, there may be too many cycles to consider. In the simple example shown here, I've given the voltage equations for the 3-cycle VXYV on the left, the 3-cycle VWYV at the top, and the 4-cycle VWYXV. But the last of these cycles is simply the sum of the previous 2, and so we don't need to consider it. Now, in his 1847 paper, Kirchhoff simplified the whole process by introducing the idea of a spanning tree through all the vertices. The only cycles we then need to consider are those obtained by adding to this spanning tree a single edge that's not in the tree. These are the 4 cycles obtained by adding separately, first the edge XY to give the left-hand cycle, WY to give the top cycle, and similarly the edges VW and YZ. Next slide, please. Much early work on tree counting was done by the algebraist Arthur Cayley, known for introducing matrices, together with his friend James Joseph Sylvester. And in 1857 and 59, Cayley began to count rooted trees, and then the harder problem of counting unrooted ones, eventually presenting his results in the 1881 paper on the right. Next slide, please. In particular, to count rooted trees, AN, where N is the number of branches, he first cut off the root, leaving several new rooted trees below it. This then led to a specific equation for the generating function shown below, from which he could then calculate, one at a time, the numbers AN. Next slide, please. Cayley then applied his tree counting methods to the enumeration of certain hydrocarbons, that is, to trees where every vertex has degree 4 for carbon or 1 for hydrogen, and also of some other molecules. And here's a list of his chemical papers. We don't normally think of him as writing papers on chemistry. Next slide, please. A later paper of Cayley's presented a number of labeled trees with N vertices, and here there's a simple answer, N to the N minus 2. So for 4 vertices, there are 4 squared equals 16 labeled trees as shown here. And for 5 vertices, there are 5 cubed equals 125. Next slide, please. Sylvester, meanwhile, was trying to link the study of chemical molecules with that of the invariants arising in algebra. Invariant theory was a popular mathematical topic of the time. And in doing so, he stated in the last paragraph that every invariant and covariant thus becomes expressible by a graph, meaning our earlier molecule diagrams. And this was the first appearance of the word graph in the sense of graph theory. Next slide, please. Other graphs that arose through their applications were interval graphs. Given some intervals on the real line, we can form a graph whose vertices correspond to the intervals, with two vertices joined whenever the intervals overlap. So here, the vertex 0, 3 is joined to 2, 7, but not to 6, 8. Such graphs have arisen when assigning bands of frequencies to radio channels, such as 92 to 95 and 101 to 103 megahertz for Radio 4, or to police car radio systems in a locality. They've also arisen in archaeology and the dating of classical writings, and also in developmental psychology and genetics, before they became mathematical objects of interest in their own right. Next slide, please. For example, the archaeologists of Flinders Petrie in Victorian times attempted to arrange 900 ancient Egyptian graves in chronological order by comparing the artifacts found in them, on the assumption that if two types of artifacts were found in the same grave, then their time periods probably overlapped. In some cases, this was done by drawing a comparability graph, where the vertices correspond to the artifacts and the edges link pairs of artifacts from the same grave. And by representing this as an interval graph, with the intervals representing appropriate intervals of time, several such seriation problems were successfully solved. In developmental psychology, the same method has been applied to the investigation of personality traits present in children as they grow up. Here you just replace artifact by personality characteristic, and you replace in the same grave by in the same child. Next slide, please. Can we characterize interval graphs mathematically? On the left is another interval graph arising from the intervals below it. We note that the 4 cycle, with vertices A, B, C, D on the left, has a diagonal bisecting it, as do all the other 4 cycles. More generally, every interval graph is triangulated in that any cycle with 4 edges or more has a diagonal, and so the cycle can be split into triangles. Any interval graph is also an incomparability graph. These are graphs that arise from a partially ordered set by joining 2 vertices when they're not immediately comparable, such as G and H at the top, or B and D below. And it turns out that a graph is an interval graph if and only if it has these 2 properties, 1 and 2. Next slide, please. Moving on to optimization problems, I'd like to mention 3 of these. In the minimum connector problem, or minimum spanning tree problem, we wish to connect towns or cities by links, such as canals or railway lines, so that the total connection cost is as small as possible. We certainly mustn't include cycles in our connections, because removing any edge from a cycle lowers the total cost. So what we seek is a tree that connects all the cities. That is a spanning tree. And below is a simple example with 5 cities A to E, where the numbers might be the distances between the cities or the construction costs. But by Cayley's result for label trees, there are 5 cubes equals 125 trees linking these cities. So which tree gives the lowest possible cost? On the right are 3 possible trees where the total costs are 23 for the first, then 21 and 20. But can we do any better than this without checking all 125 trees? Next slide, please. To do so, we use a greedy algorithm where at each stage we greedily select the cheapest link available, as long as we create no cycles. So here, we first choose the cheapest link AE with cost 2, and then the link EC with cost 3. But we cannot select the next cheapest link, AC with cost 4, because this creates the cycle AECA. So instead, we choose the next cheapest link, CB with cost 5. But then we're stuck again because AB and EB, each with cost 6, create cycles. So we have to ignore them. Instead, we choose the next cheapest link, which is ED with cost 7. And this completes our tree with total cost 17, which is better than our earliest trees. And although it's not obvious that the greedy algorithm must produce a minimum cost tree, it always does. Next slide, please. Such a way of constructing minimal cost trees was introduced by Czech mathematicians in the 1920s and was then later revived in America in the 1950s. Here it's been used to find the shortest tree joining the 48 connected US states, excluding Alaska and Hawaii. Next slide, please. A well-known problem that may sound similar, but is very different in practice, dates back to the 19th century. Here, a traveling salesman wishes to make a circular tour of some cities while keeping the total traveling cost to a minimum. This time, we seek not a minimum cost tree, but a minimum cost cycle through all the vertices, the so-called Hamiltonian cycle. Well, here are the same 5 cities, together with 3 cycles that I found, with total cost of 29, 29, and 28. But is there a better solution? Well, using trial and error, I found the one below, with total cost 26, which seems to be the optimum. But unlike the previous problem, where an easy-to-apply algorithm provides a solution, none is known here, although there are heuristic methods that produce good approximations to the best route, but no cast iron algorithm. Next slide, please. For example, it took some time before this least cost cycle around the 48 United States was found, but this was by computer. Next slide, please. Another problem arose in connection with the flow of traffic through a railway network. In 1954, the US Air Force commissioned Ted Harris and Frank Ross to find the maximum flow of traffic, train traffic, from the Soviet Union to Eastern Europe. They calculated this to be 163,000 tons, and they also located a bottleneck of the same capacity through which it had to flow. Next slide, please. This topic was developed in the 1950s, especially by Lester Ford and D.R. Fulkerson, who would then write this classic book on the subject shown on the right. At the top left is a simple network where the number on each arc is its capacity, the maximum flow of a commodity along that arc. And the aim is to send as much of the commodity as possible from the source S on the left to the terminus T on the right. And on the right, the bold numbers give a possible flow through the network, with the flow along no arc exceeding its capacity, and with the total flow into each intermediate point equaling the total flow out of it. So in the middle, SB has capacity 70, and there is 30 flowing through it. The total amount or value of this flow is 40 plus 30 plus 30 equals 100 units. Is that a maximum flow? Well, increasing the flow along certain paths then leads eventually to the third diagram, which is a maximum flow, and it has value 40 plus 66 plus 30 equals 136 units. Ford and Fulkerson's main achievement was the all-important max flow mean cut theorem. A cut is a set of arcs separating S from T, such as the arc shown in green, through which at most 40 plus 70 plus 30 equal 140 units can flow. It's clear that no flow can exceed the total capacity of any cut. In particular, that the maximum value of a flow cannot exceed the minimum value of a cut. Ford and Fulkerson proved that these two numbers are always equal. And the fourth diagram shows our maximum flow with value 136, and in pink, a minimum cut with total capacity 40 plus 12 plus 48 plus 36, again, which is also 136. Next slide, please. With the rise of computers from the 1950s, the efficiency of algorithms became increasingly important. And from the start, graph algorithms have played a crucial role in such investigations. For example, for the minimum connector problem, the greedy algorithm is efficient in that the running time on a computer for a problem with n cities is of the order of n squared. And similarly, for a network flow problem, it's of the order of n cubed. But for the traveling salesman problem, no similar result has been found or is believed to exist. This led to the definition shown here. Polynomial time algorithms, generally considered efficient, are those whose running time is of the order of n to the k, the some number k. Whereas exponential time algorithms have running times of the order k to the n for some k, such as 2 to the n or 3 to the n, and are generally inefficient. For example, let's compare the running times for n cubed and 2 to the n on a computer performing 1 million operations per second. When n is 10, these numbers are both around 1,000, with a running time of 0.001 seconds. But when n is 50, the running times for n cubed are less than a second, but for 2 to the n are over 35 years. Next slide, please. With this in mind, we let P be the set of problems that can be solved in polynomial time, such as the minimum connector and network flow problems. And we let NP be the larger set of problems for which a proposed solution can be checked in polynomial time. And this does include the traveling salesman problem. It's clear that P is contained in NP, but the big problem proposed by Jack Edmonds above and still unsolved is, are they equal? A major advance was made in 1971 by Stephen Cook in the middle, who considered a specific NP problem in logic called the satisfiability problem. And he proved the startling result that every NP problem can be changed into this problem in polynomial time. Cook also called an NP problem NP complete if its solution in polynomial time implies that every NP problem can be solved can also be solved in polynomial time. There are thousands of really important problems of this kind, such as the traveling salesman problem and the problem of finding whether a graph has a Hamiltonian cycle. And many of these problems, hundreds of them, are discussed in this classic book by Gary and Johnson. And if any one of these problems were to be proved to have no polynomial algorithm as expected, then the same would be true for all of them. Thanks in substantial measure to graph theory, the study of complexity has now become an important branch of pure mathematics, while the P versus NP problem remains arguably the most important unsolved problem in the whole of mathematics. To my mind, even more so than proving the Riemann hypothesis. Next slide, please. Finally, if you wish to read more about graph theory and its history, may I recommend, with no modesty whatsoever, these three books the third of which was published only last month. Thank you for listening.